Hi, this is Alix Paultre with AspenCore, and I'm here with Bob Beachler of BrainChip. Hi, Bob. We've been friends for a while, but this is the first time we've had a chance to talk with your new company.
Yeah, hi, Alex. Great to see you again.
Well, you know me, I love talking about the technology. And right now, you've got something really interesting in neural networks. But, well, first, I'm really glad you're doing this. And how long has BrainChip been around?
We were actually founded in 2013. We're publicly traded on the Australian Stock Exchange as an alternative way of raising funding, but it's working well for us. We've raised about $30 million US to date. I've been now with BrainChip just about a year and a half. Previously, I was with XR when we first met, and most recently I was at Xilinx working on some machine learning and embedded vision applications. So it really tied into when I was asked to come to BrainChip to work on these neuromorphic computing technologies.
Now, okay, let's back up a little bit and start talk a little bit about neuromorphic. I don't want to go into it deeply because we could talk all day about it, but a lot of people, when they think of artificial intelligence, neural networks, they think of it as a software thing, maybe some hardware, but we're really talking about a sea change in architectures and everything, aren't we?
Yeah, we really are, because with the advent of neural networks and the fact that they can do things that deterministic programming doesn't do, it's really opened up new applications. The issue with it is that it breaks the von Neumann architecture. It wants to be a distributed feed-forward approach, not a sequential step and repeat that you see in x86 or RISC processors. So now you're seeing a real explosion of new companies and even existing companies looking at new ways to do computational architectures to really implement these neural networks.
Well, and that's one of the things you're doing, because I understand you're going into a completely different direction, but in a more challenging direction with your spike network. So can you explain a little difference between what you're doing and what's being done right now?
Sure. So spiking neural networks are the third generation of neural networks. Convolutional neural networks is kind of what probably 95% of the industry is focused on right now, because that's what AlixNet did with the ImageNet challenge in 2012. Spiking neural networks, instead of using convolutions like AlixNet, which is a math function, we're doing it by emulating the biology of the neuron. So we're inspired by that, but doing it in a pure digital process, but we're preserving the characteristics of a biological neuron. It provides us with a really low power way of doing similar functionality, but much more efficiently, so that you can put it in like a sub 1 watt device and put it in the edge.
Now, you had explained it a little bit earlier, and I want to make sure that you make it very clear to the audience that the spike aspect actually explains a significant aspect of the process.
Yeah, sure. So spiking neural networks are modeled on neurons. Neurons operate in spikes. It's a spike between synapses. However, you need to get everything into spike data. The human body does that automatically. The retina, your ears, the olfactory process, those sensory organs transmit spikes to your brain. Similarly, we have to do a similar data to spike conversion for industrial applications. So for example, if you're using CMOS image sensors, a pixel, we have to convert those pixels into spikes. If you're using big data, like in financial technology, if you're doing cybersecurity where you're looking at file parameters, we transform that data into spikes so that that data can then be used to train our neural networks. And then when we run it in inference mode, we can take the data, convert it to spikes, and do the object classification, do anomaly detection, do pattern recognition, and the like.
Right. Now, I understand you've consolidated all of this into and manifested it in a product. You have an actual chip now that can do all of this.
Yeah, that's the Akida Neuromorphic System-on-Chip. And it's really important that, we're calling it a system on a chip because we've had to put all of the aspects, the data to spike converters, the actual neuron fabric that does the computation, the emulation of the neurons. We have some supervisory processing. We also have all the IOs for inputs for different types of sensors, like pixel data, LiDAR data, ultrasound data, acoustic data. We have to be able to take all of that in, do sensor fusion, train our networks, and then execute it on the chip.
And that's also very interesting, the whole aspect of having to train a neural network device, because that's an aspect that people didn't think about before. I could just program it and it'll run, but there's actually a learning and acquisition process involved in this.
Yeah, and that's really important to understand, which is how good your neural network functions is a function of three things: the architecture of the network, the data set that you train it on, and the training methodology that's used. If any of those three things are out of whack, you end up with a dumb network, and it's not going to perform to the performance or accuracy that you need. Many companies, many of our customers feel that their proprietary advantage is going to be the data set that they have, because they have better data, they've processed it so that their data sets will train neural networks to be better than somebody who doesn't have access to the same levels of data.
Right. But now, in your case, you've actually taken your IP, you've taken the topology and the software, and you've manifested in a product. Can you tell us a little bit more, how big is the chip, what's its power capacity, what is its processing capability?
Yeah, so the characteristic of a spiking neural network is that it's low power. So we're designing it to be used in edge applications. It's a sub 1 watt device. However, we're putting on an expansion bus so that we could put multiple devices together so that we could scale it for cloud server applications for people who want to do very large data processing and using really large neural networks.
Mm-hmm. So, and I understand you're going to be releasing this chip sometime next year. How big is it going to be? What's going to be the ballpark price, or can you disclose that kind of information at this point?
Yeah, we're not really disclosing that at this point, and because a lot of it has to do with depending upon what the process technologies look like at the time and what the wafer costs. We're process agnostic. We use standard CMOS digital logic process, so we're going to be able to shop for the best process technology at that time, and whether it's 14 nanometer with a smaller die size but higher wafer costs, we may use 28 nanometer, which will be a little bit higher die size, but the wafer costs might be less and the yields are better. So we really have that flexibility. So we're not quite disclosing that, but we're going to be pricing it for volume production. This is not any type of evaluation test chip. It's not a $1,000 test chip. We're talking about, on the order of $10 to $15 type of areas so that it can be used in industrial applications.
From the core to the edge.
Oh, absolutely. Yeah, and that's, again, that flexibility standpoint to be able to put multiple devices together. There's also tricks you can do in terms of time division multiplexing the network into it, so you could process 5 layers, save it, bring in the next 5 layers, do it again. You wouldn't get the same amount of, say, throughput, but you may be more efficient and have a lower total cost on your BOM.
Very nice. Now, Bob, you had mentioned 3 primary areas: machine vision, security, and financial. Can you give me an example out of each of those bins?
Sure. So in vision applications, whether it's vision-guided robotics, whether it's ADAS, autonomous vehicles, you're really doing object classification based upon the visual spectrum, or even, say, LiDAR data or ultrasound data. So you're doing a classic object recognition. So you would start with a neural network that is set up to architect for object recognition in an embedded environment. Whereas in, for example, financial technology, this is primarily done in IT server rooms. So in that case, you're a co-processor, perhaps on a PCI Express card, and you're analyzing parameters of stock characteristics, whether it's beta, volume, pricing, you're looking at economic indicators, and in an unsupervised mode, you have your neural network cluster these patterns into areas, and then you analyze those clusters to see, gee, this cluster means that the price is going to go up, or these economic indicators tend to show that things are going to go down, and you can use that to be more intelligent in balancing your portfolio. The final application would be in cybersecurity, where I look at file parameters or packets, and I can look at the parameters and have known good parameters and known parameters that may be malware. Then I do in a supervised training mode, set up a file classifier. When I see these parameters, it's a good file. When I see these parameters, it could be malware, right? And now I have the ability to do a zero-day malware detection because I'm able to look at the parameters, the meta parameters, as opposed to doing a file signature, which is what kind of your traditional antivirus software does.
Mm-hmm. Well, then it's the whole aspect of detecting change, as it were. I think I'd earlier mentioned it's kind of like almost a high definition image compression in reverse. Instead of compressing it so only the changes are seen, you're capturing only the changes.
Yeah, sure. And so part of what we do with data to spike conversion, we compress the data down into spikes like the brain does. The brain processes spikes, and as you go through each layer, you have less and less spikes. Therefore, we only process when we have a spike, so it reduces our overall computational load. In the neuroscience world, this concept is called sparsity, right? And so you have a sparsity of spikes, you use less power. The brain uses 20 watts, and it's the most intelligent thing on the planet, right? We're not even close to that yet in terms of the capability of the chips, but by emulating that technology, we're able to get the efficiencies.
Very nice. Okay, so Bob, we're here, we've got this, it's on the horizon. Is there anything you can tell our audience as far as anticipation or, wait for it kind of thing? Because there's a lot of buzz about neural networks and neural processing and all. So what would you like to leave our audience with so they know to wait for you?
Yeah, sure. Well, I think one of the things is that as the third generation of neural networks, spiking neural networks, it's new. It's kind of the path less chosen compared to what the people are doing in the convolutional space. That's why we've announced early access to our Akida development environment, which allows people to get the development environment, be able to start experimenting, look at neural networks, see how they're trained, see how they perform, so that when the silicon's available in about 12 months, they'll already have their networks. This is something I borrowed from my FPGA days. You always wanted to get the development tools out just about a year before you actually sampled the silicon, so that people had their designs, they knew what performance to expect, and then when the silicon was available, they had their designs done and they were ready to go.
Very cool, Bob. So then, you're looking for partners, you're looking for people. How do they reach you?
So we're available www.brainchip.ai, brainchipinc.com. We're on LinkedIn. And so, this is kind of our big coming out party from a semiconductor standpoint. We've done this type of neuromorphic computing in other technologies and software and in FPGA acceleration cards, but now this is really the new thing for us.
Excellent. I'm really looking forward to seeing the device, and I imagine our audience is as well. Thanks for the time.
All right. Thank you, Alex. Great to see you again.